Hello, this paper presents a study on low grid voltage problem near Rooppur nuclear power plant. The research was conducted by Dr. Abdul Hazib Chowdhury and Mohammed Karam Moni Rabi from the Department of Electrical and Electronic Engineering, in short called EE, at Bangladesh University of Engineering and Technology, in short called BUET, Bangladesh. The main concern is the risk of Rooppur nuclear power plant tripping due to low bus voltage, especially under small loading conditions. This study uses the existing Bangladesh Power System Network, called BPSN, as the basis for analysis. The grid directly affects the nuclear power plant, called as NPP, is startup and operation, so identifying vulnerable buses is critical. Our objective is to use continuation power flow, CPF, analysis to locate low-voltage buses in the western grid near Rooppur. IEEE standards define safe operating voltage ranges for NPP equipment. For example, high-voltage motors can operate down to 75% of nominal voltage during startup, while low-voltage motors can go to 70%. Valve drives require at least 80%. Backup diesel generators can tolerate 15 to 20% voltage drops. Note, continuous operation at these levels is not acceptable. Transformer tap changers can compensate for off-nominal voltages within plus or minus 10 to 15%. Low voltage in the grid can result from several factors, such as slow fault clearance by protection systems, long transmission lines without intermediate support, lack of voltage control devices like synchronous condensers or capacitors, absence of on-load tap changers, and insufficient line capacity during peak load. A sharp voltage drop is often experienced due to transmission line faults, depending on fault proximity, AVR sensitivity, and relay response time. Motors may stall during such dips. Prolonged low voltage complicates the startup and operation of large NPP motors, some of which have flywheels and extended start times. Voltage stability depends on reactive power balance. Without proper tap changers, safety bus voltages can fluctuate. Undervoltage can trigger thermal protection in motors, cause relay malfunctions, and degrade safety system performance. The Bangladesh power system is divided into 5 regions. The western grid includes northern and western zones, while the eastern grid covers Dhaka, central, and southern regions. Power is generated in the east and transmitted to the west via two 230 kV tie lines, Gorasla-Turbai and Ashaganj-Sirajanj. This geographical and electrical layout forms the basis of our modeling. This slide shows the reduced east and western interconnection system with Rooppur NPP integrated. The 2 critical tie lines are highlighted. Bulk power transfer from the eastern to western grid is essential for maintaining voltage stability near Rooppur. Load behavior is modeled using exponential voltage-dependent equations. Active and reactive power at a bus depend on voltage exponents A and B. This representation helps simulate how voltage drops affect load demand and system stability. We used bifurcation analysis, specifically saddle node bifurcation, via UPFlow software. This method helps identify voltage collapse points as load increases. The graph illustrates the voltage power curve, with the saddle node indicating the stability limit. Rooppur NPP is connected to the Ashurdi bus. Therefore, if Iturbay and neighboring buses like Baramara, Rajarshi, Pabna, Bageri, and Nator experience low voltage, the NPP will also be affected. This makes voltage monitoring in these areas critical. This table lists key transmission lines near Rooppur, including voltages, lengths, and route circuits. Long lines like Gorasla-Shirdi, which length is approximately 178 km, are especially vulnerable to voltage drops, impacting nearby buses. The table shows loading factors and actual minimum voltages for selected buses. Buses with low loading, like Barisal and Faridpur, maintain voltages above 0.8 per unit. However, buses with high loading, such as Pandaria and Chapinawabganj, already operate below 0.8 per unit. This indicates that even small load increases could push these buses into critical undervoltage conditions. Our analysis confirms that buses near Rooppur NPP are at risk of low voltage. Beyond 0.8 per unit, increasing load factor causes rapid voltage decline, leaving insufficient time for system recovery. This poses a real threat to NPP operational safety. We recommend further studies on dynamic system behavior and smart grid solutions to mitigate low-voltage risks. This could include real-time monitoring, adaptive protection schemes, and enhanced reactive power support. The research on low grid voltage problem near nuclear power plant is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.